Hello, my name is Adi Dahake, and in this tutorial we're going to learn how to find areas using polar coordinates. This is a fundamental calculus topic that combines polar coordinates with integration. We'll start with the basics concepts, derive formulas, and work through several examples. By the end, you'll understand how to solve any polar area problem. Let's start with a quick review of polar coordinates. Here are some basic conversions that you must have a good understanding of. Remember that polar coordinates use a radius r and an angle theta. The conversion formulas are x equals r cosine theta and y equals r sine theta. Going the other way, r equals the square root of x squared plus y squared and theta equals arctangent of y over x. Here is the polar coordinate system. We have circles for constant r values and lines for constant theta values. The grid structure is important for understanding how we break down regions for area calculations. Let's look at a specific point with polar coordinates 2, pi over 3. Using our conversion formulas, its Cartesian coordinates are 1, root 3. The radius r gives us the distance from the origin and theta gives us the direction. Here are some common polar curves you'll see in area problems. First, a simple circle with the equation r equals 2 in this case. This creates a circle centered at the origin with radius 2. Next, a cardioid, in this case with the equation r equals 1 plus cosine theta. This heart-shaped curve shows how the radius changes with the angle. Finally, a 3-petaled rose, in this case with the equation r equals 2 cosine 3 theta. This demonstrates how periodic functions create symmetric patterns. The key point for area calculations is that each polar curve r equals f of theta traces a path as theta varies. Unlike Cartesian coordinates where we integrate with respect to x or y, polar coordinates naturally lead us to integrate with respect to theta. Now let's derive the formula for finding areas in polar coordinates. We'll use the fundamental calculus approach of breaking complex regions into smaller pieces. We know that the area of a circle with radius r is pi r squared. But what about irregular polar curves? The key is to break these regions into manageable pieces. Here's the idea. We can break any polar region into thin sectors, like slicing a pie. Each sector is approximately a piece of the circle, so we can use our knowledge of circular sectors. Let's examine a single sector. For a circular sector with r and a central angle delta theta, the angle is sector angle over 2 pi times pi r squared. That gives us delta theta over 2 pi times pi r squared. This simplifies to 1/2 r squared delta theta. Now comes the calculus. As delta theta approaches 0, our sector becomes infinitesimally thin. The area of this differential sector is dA equals 1/2 r squared d theta. This is our building block. For polar curves, the radius isn't constant. It varies with the angle. We write this as r equals f of theta. So our differentiable area element becomes dA equals 1/2 times f of theta squared times d theta. To find the total area, we integrate these differential elements over the range of angles. This gives us a equals the integration from alpha to beta of 1/2 times f of theta squared d theta. We can factor out the constants. A equals 1/2 times the integral from alpha to beta of r squared d theta. Here's what we just did. We sliced the region into infinitely thin sectors. Each sector has an area 1/2 r squared d theta. Integration adds up all these tiny areas to give us the total. Now let's use this formula in a real example. Let's solve the problem. Find the area enclosed by the curve r equals 2 cosine theta from theta equals 0 to theta equals pi over 2. First, let's see what we're working with. The curve r equals 2 cosine theta creates this shape. Notice that when theta is equal to 0, r is equal to 2. When theta is equal to pi over 2, r is equal to 0. Here's the region we want to find the area of. It's bounded by the curve, the ray theta equals 0, and the ray theta equals pi over 2. Now we apply our polar area formula. A equals 1/2 times the integral from 0 to pi over 2 of r squared d theta. Substituting our function, a equals 1/2 times the integral from 0 to pi over 2 of 2 cosine theta squared d theta. This becomes a equals 1/2 times the integral from 0 to pi over 2 of 4 cosine squared theta d theta. Simplifying, a equals 2 times the integral from 0 to pi over 2 cosine squared theta d theta. To evaluate this integral, we can use a useful trigonometric identity, which is the double angle identity for cosine. When we rearrange that identity, we get cosine squared theta equals 1 plus cosine 2 theta over 2. When the double angle identity is rearranged, it is sometimes referred to as the power reducing formulas, and these formulas can be pretty helpful when trying to find the area of certain polar curves. Substituting this identity, a equals 2 times the integral from 0 to pi over 2 of 1 plus cosine 2 theta over 2 d theta. This simplifies to a equals the integral from 0 to pi over 2 of 1 plus cosine 2 theta d theta. The antiderivative is theta plus sine 2 theta over 2 evaluated from 0 to pi over 2. Evaluating at the bounds, at pi over 2, we get pi over 2 plus sine pi over 2, which is pi over 2 plus 0. At 0, we get 0 plus sine 0 over 2, which is 0. Therefore, a equals pi over 2 minus 0, which is equal to pi over 2. This result should make intuitive sense because the curve r equals 2 cosine theta is actually a circle, with the center at 1, 0 and a radius of 1. Our region is a semicircle with radius 1, so its area should indeed be pi over 2. Now let's work with a more complex example. Finding the area of one petal of a rose curve, r equals 3 sine 2 theta, from theta equals 0 to theta equals pi over 2. First, let's see the complete rose curve. The equation r equals 3 sine 2 theta creates this 4-petaled rose. Each petal is identical due to the symmetry of the sine function, so finding the area of one petal tells us about all of them. Here's the single petal we're analyzing, traced from theta is equal to 0 to theta is equal to pi over 2. Notice the behavior at theta is equal to 0, r equals 3 sine 0, which is 0. At theta is equal to pi over 4, r is equal to 3 sine pi over 2, which is 3. This is the maximum. At theta is equal to pi over 2, r is equal to 3 sine pi, which is 0 again. So the petal starts at the origin, reaches the maximum distance, then returns to the origin. Now let's apply our area formula to find the petal's area. Using the polar area formula, a equals 1/2 times the integral from 0 to pi over 2 of r squared d theta. Then substituting our function, a equals 1/2 times the integral from 0 to pi over 2 of 3 sine 2 theta squared d theta. This becomes a equals 1/2 times the integral from 0 to pi over 2 of 9 sine squared 2 theta d theta. Then factoring, a equals 9 over 2 times the integral from 0 to pi over 2 of sine squared 2 theta d theta. For sine squared 2 theta, we use the identity sine squared 2 theta equals 1 minus cosine 4 theta over 2. Substituting, a equals 9 over 4 times the integral from 0 to pi over 2 of 1 minus cosine 4 theta d theta. Now integrating, we get a equals 9 over 4 times 0 minus sine 4 theta over 4 evaluated from 0 to pi over 2. At pi over 2, we get pi over 2 minus sine 2 pi over 4, which is pi over 2 minus 0. Then at 0, we get 0 minus sine 0 over 4, which is 0. Therefore, a equals 9 over 4 times pi over 2, which is equal to 9 pi over 8. Since there are 4 identical petals, the total area of the entire rose curve would be 4 times 9 pi over 8, which is equal to 9 pi over 2. This demonstrates the power of symmetry in polar coordinates. Some key points to remember: choose your integration bounds carefully to capture exactly one complete petal. For rose curves with the equation r equals a sine n theta, where n is odd, you get n petals, and when n is even, you get 2 n petals. And finally, each petal has the same area due to symmetry. We have now seen how to find areas inside single curves, but what if we need to find the area between 2 different polar curves? Here we have 2 polar curves, an outer curve with the equation r equals r outer of theta and an inner curve with the equation r equals r inner of theta. The shaded region is the area we want to find. The approach is straightforward. The area between the curves equals the area enclosed by the outer curve minus the area enclosed by the inner curve. Same principle we use for the Cartesian coordinates. Let's write this out. The area enclosed by the outer curve is A outer equals 1/2 times the integral from alpha to beta of R outer squared d theta. The area enclosed by the inner curve is A inner equals 1/2 times the integral from alpha to beta of R's inner squared d theta. The area between them is A between equals A outer minus A inner. Substituting our equations, A equals 1/2 times the integral from alpha to beta of R outer squared d theta minus 1/2 times the integral from alpha to beta of R inner squared d theta. Since both integrals have the same limit and the same factor of 1/2, we can combine them. A equals 1/2 times the integral from alpha to beta of R outer squared minus R inner squared d theta. This gives us our formula of the area between two polar curves. A equals 1/2 times the integral from alpha to beta of R outer squared minus R inner squared d theta. Use this whenever you have two curves and we want to find the area between them. Here's a challenge. Find the area between the limacone R equals 3 plus 2 sine theta and the circle R equals 2 in the upper region. Let's see both curves. The limacone R equals 3 plus 2 sine theta creates this heart-shaped curve. The circle R equals 2 is centered at the origin. We can see these curves intersect at 2 points and we want to find the area between them in the upper region. First, we need to find where the curves intersect, setting them equal. 3 plus 2 sine theta equals 2. This gives us 2 sine theta equals -1, so sine theta equals -1/2. This happens at theta equals 7 pi over 6 and theta equals 11 pi over 6. Here's something important. We want to find the upper region, so we need to choose our bounds carefully. We should integrate from -pi over 6 to 7 pi over 6. This ensures we enclose the correct shaded area. If we used 7 pi over 6 to 11 pi over 6, we would get the bottom region instead. Now we apply our formula. A equals the integral from -pi over 6 to 7 pi over 6 of 1/2 times the limacone squared minus the circle squared d theta. That's A equals the integral from -pi over 6 to 7 pi over 6 of 1/2 times 3 plus 2 sine theta squared minus 4 d theta. Expanding this, it becomes 1/2 times the integral of 9 plus 12 sine theta plus 4 sine squared theta minus 4 d theta. Simplifying this, A equals 1/2 times the integral of 5 plus 12 sine theta plus 4 sine squared theta d theta. For sine squared theta, we use the identity sine squared theta equals 1 minus cosine 2 theta over 2. Substituting this, we get A equals 1/2 times the integral of 5 plus 12 sine theta plus 2 of 1 minus cosine 2 theta d theta. This simplifies to A equals 1/2 times the integral of 7 plus 12 sine theta minus 2 cosine 2 theta d theta. Now integrating, A equals 1/2 times 7 theta minus 12 cosine theta minus sine 2 theta, evaluated from -pi over 6 to 7 pi over 6. Now evaluating the bounds and simplifying, we get A equals 11 root 3 over 2 plus 14 pi over 3, which is approximately 24.187. Here are some key takeaways. The bounds determine the region you calculate. Using pi over 6 to 7 pi over 6 gave us the upper area, but using 7 pi over 6 to 11 pi over 6 would have given us the bottom area. So it's always important to check the region visually. Now let's review the key concepts for finding area and polar coordinates. The core principle is to break regions into infinitesimal sectors. There are three main scenarios. First, area inside one curve. Second, area between two curves. And third, partial regions with specific bounds determined by intersection points. Here are some tips for getting questions correct. First, visualize the curves in order to prevent errors. You can also find the intersection points by setting the curves equal to each other and solving for theta. And this allows you to choose the bounds wisely, as integration limits determine which region you calculate. Finally, apply trigonometric identities if necessary to simplify the integration. Some common mistakes to avoid are using the wrong integration bounds, so I always double check, forgetting the 1/2 factor in the area formula, and mixing up the inner and outer curves. Always subtract smaller from larger. Here's a good problem-solving checklist. Identify the curves and sketch the region. Find intersection points if needed. Determine integration bounds. Choose the appropriate area formula. Substitute r theta and integrate. Verify your answer makes geometric sense. Polar area problems combine geometric understanding with calculus integration. Practice different curve types and you'll master these kind of problems. I hope this helped you understand how to approach these problems, and thank you for watching this tutorial on area and polar coordinates.